problem 72 added distance. Okay, looks like we're live. Hello world, my name is Alan. We're doing live LeetCode practice. Today it's our month 3 and we are doing this problem that's so in the dynamic programming group. Let me, oh, I think I'm sharing the wrong one. Yes, so this one is problem. Yeah, so we are working on dynamic programming topic, and there is this problem number 72, added distance. Given two strings, word 1 and word 2, return the minimum number of operations required to convert word 1 to word 2. You have the following 3 operations permitted on a word: insert a character, delete a character, and replace a character. Let's check out some examples. Word 1, horse. Word 2, Ross. Okay, so if we do some replacement, like we replace H with R, that will give us roars. Then we remove R, it will be a rose. And then we remove E, it will be a rose. Okay, so I guess I kind of understand the operations now. Replacement, if you take one letter and replace it with another letter, and it looks like we can only do it for one character at a time. Words: intention, execution. Okay, we'll do some replace, insert. And we get our execution. The length is up to 500. It consists of lowercase English letters. Do we have our, I should restart the clock. Okay, so return the minimum number of operations required to convert. Well, I'm reading this book and it says that any dynamic programming algorithm, to develop a dynamic programming algorithm, follow a sequence of 4 steps: characterize the structure of an optimal solution, recursively define the value of an optimal solution, compute the value, typically in a bottom-up fashion, value of an optimal solution, construct an optimal solution from computed information. Well, okay, so dynamic programming algorithms, they use this solved sub problem. They use a shared sub problem. Yeah, like if you have one subproblem solved and it's overlapping with another, it's helpful. Its solution is helpful for another subproblem. So there is an overlap. Then we can use that instead of redoing that subproblem. And the word programming in the term dynamic programming doesn't stand for writing computer programs. It stands for, the meaning is tabular It refers to the tabular method. So you write a table of values, and there are tons of interesting things to read here. There's like this chapter in this book is like 30 pages. So, but let's see what we can do with this problem. So, horse, Ross. I wonder if we can take a minimum subproblem, and let's say like we have let's say we have the minimum would be like, I don't know, if we like I'm just trying to pick some words that I would like to work on. We want to find the minimum number of operations required. Minimum number. To convert, okay, so we're always converting word 1 to word 2, but somehow I feel like converting in reverse will have the same number of operations. For somehow I feel so. Yeah, so let's say we have A, we need to convert it to B. What is the, we just need to do one replacement and we're done. If we have a C, we need to convert it to B. Then okay, how can we use that? We know we can do that in one operation, so we have additional C, which means we need to, in this case, we would need to remove C after converting A, and it will be 2 operations. One op, 2 ops. Now, if it's A, B, if it's A, C, D, ACD, then it's what? Well, we know we need at least 2, so D adds another 1, so it will be 3 ops. And so on, and so on. Well, this looks pretty linear. This looks pretty linear to me. Okay, so the goal I have right now is, let's lower our expectations. The goal now is just to see if I can come up with a logical approach with the logic of the solution, because I'm kind of new to these multi-dimensional dynamic programming, and yeah, sometimes, by the way, sometimes they're solved with tabular. So let's say if we have this tabular approach, so if we take that horse, and at the top we'll have the horse, and then we have on the left side we'll have this Ross. So the question is, what is the minimum number of operations? What is the sub-problem? I'm trying to understand the sub-problems and how they overlap. And so, yeah, we can use that power of having those. I don't see that a tabular like that helps here. We want to, well, we can actually, if we check all the values that are not there, that are like in this case, we needed 3 operations, and we have 2 matching letters in the right order. Those letters are O and S. So O, and then S comes after that. OS. So we don't need to like change them, essentially. We do need to work on the other 3. So if we have this tabular, what if it's just simple as that? Yeah, if we just identify, because yeah, essentially if we identify all those intention is I 1, 2, 3, 4. Oh, we do need to remove this T. Oh. Yeah, so it looks like the only part that overlaps here is this TION at the end. So although E is also there is one E that, I mean, we have an E here. Its position. So, but we have these 5 letters. So this example suggests it's not just about the subsequence having this it's not just about having the longest, you're finding this longest common subsequence, which is another problem on LeetCode. Yeah, if we found this subsequence common longest and the length of it, because we have the subsequence of E and T and Shin is there, but we actually need to replace I with an E. Well, we don't. Oh, wait a second. So there is one E. We need two E's. So we are actually adding, one E. But so we remove one T. I'm trying to understand. To have this execution, why don't we, if we have an E there, why can't we do it with just four steps? Like if we can't do the swap, we need to use that E, which we are using that E, but we need to delete things and then add things, and those are into steps. Those are done into steps. But in this example of horse, we only have to we have O and we have S. So we just remove that. Well, we replace that H, and then we just remove the unnecessary stuff. In this case, we remove the T, and then we do 3 replacements and then 1 insertion. So the maximum common subsequence is not a full answer here, I have to say, from what I'm seeing so far. Because although this E is in the subsequence, it is common, but there you have to do more than just having this common subsequence doesn't mean that you can do only 4 operations. You still have to do 5 ups to get this intent to execute. The turn intent to execute, which is essentially the sub problem. And if we actually look at if we look at I wonder if we can look at this even more, if we want to turn intent to execute, we can check it out and see what is actually happening here. Why can't I maximize this thing? Okay, so that's so what will it take to turn this thing, because yeah, we do have the E already existing, but yeah, we need another E. So we have E, then we'll need but that E is not in the right place, so we'll need to remove yeah, we'll need to remove one of the, yeah, like E or N, and then replace, yeah, the E is here, so, oh, then it's here. Wait a minute. Yeah, when we want to turn to execute, so we actually will need to add this, like replace N with C, and then add U, insert U, yeah, and then replace these two. And T we need to remove because, or whatever, any of these three, one of them we need to remove, because we can't do the swap, like move T onto the other end. It's a two operations thing, because E is not in the right position. Yeah, I need to move it. And for this example, the difference is so we have essentially, yeah, so look at that. We just need to remove these two and replace this H, yeah, which is what's happening here. Yeah. So I'm trying to like see like what are the sub problems if we have some 10 execute. We see like the first letter character, first character, they don't, I don't know if we just, okay, let's go and just start changing things. Obviously, the longest, the maximum number of ops is just to completely, like the maximum number is to like remove the whole thing and rebuild it from the start. Okay. So that will be like N plus M. Or just replace, yeah, so like, yeah, that was like N plus M, which is, yeah, 500 is the length. Yeah, but it's not going to be the shortest. Yeah, then we can do, that's number of operations. That's not algorithmic. It's not the right answer, essentially. Yeah. So it's not time complexity. It is time complexity, but it's not the right answer. Then the N minus M, if we actually like, if we just replace and then add, fully replace the overlap between them, and then add or remove whatever needs to be done. So that is that. And then there are some words in some subsequence, some letters, I mean, that we don't even have to replace. That, I guess, is the optimization that allows us to do better than that. Yeah, so find the characters, find the common subsequence characters. Yeah, that we don't have to. Yeah, we find those. It is the longest, but the thing is, it just doesn't. Yeah, what can we? The longest common subsequence is not the full answer. As we saw here, I needed to do this. It was not in the right position, so the common characters, they might need a little more, so we can use them, and the length of the common subsequence will play critical role. Yeah, because the length of it was 4 plus 1, which is 5. And then there is this 9 total. How many characters is that? 1, 2, 3, 4, 5. So essentially, we could just replace all of these 5. I mean, the E is there, but it's not in the right place. So we could just do, okay, replace that, like all 5. Replace all 5, yeah. Yeah, why mess with like... Okay, so I'm getting some better understanding of the problem, but I don't think I'm already that we are already at the core, or we have a solution ready. Let's give it a couple more minutes, and then I guess we'll take a break to think about it a little bit more. We are reaching. So the base, the common, the longest common subsequence is a dynamic problem in itself. It's one of the, it's like that we just solved yesterday. So we could use that, but it doesn't give us the answer. That's the problem, because the length of it would be 5, but it's just essentially just doesn't. How do we know that? Well, if the position and it would be like, it would be a kind of tricky to even start like comparing these parts. This suffix, postfix, okay, so essentially the B word could be a combination of, so let's say if that A is a combination of B and A. So we just need to remove A to the length of A out of B, and that's clearly, that will just that will be the answer. Yeah, just remove A to the length of A. If it's, yeah, but in this case, yeah, but the other parts could be common. Yeah, if we have like some common parts, and we just need to remove part of the A, keep the rest. It's quite an interesting problem. I'm using with some of these problems while I'm still learning the concept, I find it really helpful to just go and see the tutorials, because many of these, it's like super hard. It's almost impractical to try to solve them by yourself. And try to like so no need to reinvent the wheel here in many cases. So this might be one of those, because like I don't see immediately. I'm a little bit, I think I have some ideas of what we can reuse, but I don't see it fully yet. I don't see it so yet. So I would probably, what I would do probably, look up this solution, because this is a classic problem. This is what, first 100 LeetCode. Oh, I bet it's a classic one. So good old original problem. So how many operations? Oh, I think I even looked at the, I think just yesterday I was looking at this video, this like training for solving for solving algorithmic problems. And I think that problem was a super booper classic. I think it's even a named algorithm. Yeah. I think, yeah. Let me see. I think it's definitely one of those. Yeah, let me just check it out because I think it's definitely one of those. Let me check this. There's distance, yeah, added distance. It was right after this longest common subsequence, yeah. Yeah, this added distance. It's the distance of Liebenstein. Yeah. Yeah, the minimum number of operations of insert, delete, or add or this replacement to turn one string to another. So I have this exactly, yeah. So this explanation of about 10 minutes about it, yeah. So it's Levenstein distance. Levenstein distance. Okay, let me look at them. Look it up. Yeah, so with these problems, when studying them, I found it's really helpful to know what you know and what you don't know. Oh yeah, Levenstein distance. Yeah, that's sweet. That is so sweet. Yeah. Well, if a solution has somebody's name on it, yeah, and that was a Soviet mathematician, Vladimir Liebenstein, who defined the metric in 1965. Yeah, I wonder where he was working. Yeah, Moscow State University. He graduated in Moscow State. Nice. So it's used in information theory, linguistics, and computer science. Is a string metric for measuring the difference between two sequences. The Levenstein distance between two words is the minimum number of single character edits, insertions, deletions, or substitutions required to change one word into the other. Yeah, it may also be referred to as added distance, although that term may also denote a larger family of distance metrics known collectively as added distance. It is closely related to pairwise string alignments. Wow, pairwise string alignments. The Levenstein distance between two strings A and B. Okay, so from this moment, this video is more about learning than about solving. Well, I need to take a break to study basically this, to get some better idea of what it is. I need to watch that video, and it's about like 10 minutes to get the idea, and then probably try to solve it. But I mean, it's the full solution, so just try to kind of understand it, and so I can get comfortable with it and use it later. Well, I think that was a good exercise on remembering what I know and what I don't know. And thank you for watching, and see ya.